The Earth, our only home in the universe. We live on a planet that has an epic and violent past over billions of years. Built from fire and ice and bathed in the light of our nearest star, the Sun, our Earth is a world of constant change. Continents collide, turning layers of rock upside down. Oceans form with new wonders down in the abyss. From space, the Earth emerges as a world of water. Oceans shimmering blue and turquoise through delicate white clouds. Wrapped in a thin layer of air, the Earth provides life and all our life's needs, sheltered from the cold vacuum of space. Who are the men and women that strive to unlock the mysteries of our planet? In other words, what on earth do geologists do?
Imagine you're sitting on the edge of a potentially active volcano. If you're sitting on the edge of a volcano, you need to know when it's going to erupt, what kind of eruptions it's had in the past, what level of risk it presents to the population at large. But it's more than that. Volcanoes really are the driving force of a lot of deposition of minerals. So many mineral deposits are formed by volcanic processes. Understanding ancient volcanoes helps us understand where we might find ore deposits, but understanding ancient volcanoes also helps us understand modern volcanic systems, and if we can understand those, then we can start to look at the level of risk that people might be under when they live next to volcanoes.
Geophysics allows us to look beneath the surface of the Earth without drilling or digging. I mean, it's in a way it would be almost like Superman with his X-ray vision peering down into the Earth. We have a variety of methods that we pull in from the field of physics to study the Earth. We use magnetic fields, gravity fields, radiation, and seismology, of course, and electromagnetic fields. All of them are used to peer into the Earth and to try to image what's down there without directly digging or drilling into it. And that's very powerful. Over the last 100 years, it's revolutionized thinking really about how the Earth works, about things like plate tectonics and volcanoes and earthquakes. We understand much better how these things work.
Well, near-surface geophysics has to do more with the environmental side. I don't look for minerals. I look more for either contaminants or, in my case, I look for salt water. It's obviously important because you need to know where salt water is if you're going to have coastal communities to ensure that you do not put the salt water into your drinking water.
Where geology typically studies the surface of the Earth and rocks taken up from discrete boreholes, with geophysics you have the ability to investigate the third dimension. One
of the important things is that most of the world's population lives in or around coastal areas. And as more and more people move towards the coast, the demand on the water that we drink becomes higher and higher. And if we can tell if that water is safe to drink, that will allow us to better plan our cities, better manage our resources.
I deal with water contamination very often, so certainly I think it's pretty important that we protect our water resources against contamination. And sometimes, in fact very often, I deal with waste disposal. And the idea is to use the knowledge of water and water chemistry to prevent waste disposal from impacting our water resources. So society creates a lot of waste, we need the water, so I think there's actually a good crossover there. In the nuclear industry, I think most people are familiar that we generate waste, and the waste is long-lived, and there's concern about that waste because it could, in the future, impact on the surface environment, the hydrology, the biosphere, and so on. So I think internationally, probably the consensus is that the best way to deal with nuclear waste is to use a geologic environment, because the rocks are old, and if we can put the waste in the rocks, and if we know that the rocks are going to provide safe containment, then we can have some satisfaction that we'll take care of that waste safely for a long time.
Well, my discipline concerns the geochemistry of water, the chemical reactions of water with materials of the Earth. Water is important as a resource. The quality of the water that we drink is certainly very important to us. It's used in numerous industrial processes. The quality of the water is important there. It also plays a role in forming mineral deposits. And that's where I first got interested in aqueous geochemistry, was in terms of formation of ore deposits.
The research area that I'm mostly in is related to economic geology, a spectrum of mineral deposit types that we have here in New Brunswick that are of economic importance, but also across Canada, various mineral deposit types that my research group is involved with. They obviously have tangible aspects to discovering, exploring mineral resources, and sometimes even right into the benefaction and exploitation, for the lack of a better term, of those resources as well.
Economic geology is actually explore for and develop metallic and non-metallic resources. So what I'm doing, I'm actually using this mineral called biotite, which is a part of the granite here, these black things that you can see here, to distinguish between barren and mineralized granitic system. Granitic rocks actually forming most of our crust. And crust is where we're living on. So if this is most common rocks within the crust, finding if this is mineralized or it's not mineralized would really help us to solve a problem, because now that population is growing, we need more materials. So by doing that, we can actually save much time and money before we go further.
Lake muds, or ancient lake muds, mudstones, are important source rocks for petroleum. So we find petroleum in shales, and particularly oil shales. So the formation of petroleum is generally accepted to be the result of the breakdown of ancient algae and potentially also some larger plants such as your trees that produce coal. So your algae tend to form the oil shales, your ancient trees break down and produce your coals. One of the interests I have is looking at the fossil microbes that can be found in the oil shales.
The only evidence that we really have on the history of life is paleontological, i.e. the study of fossils. Those are the objects where paleontologists deal with. And it's also important in several more economic applications. For example, the oil industry, the oil and gas industry in fact, use fossils a lot to determine the actual age and location of oil and gas deposits. But I still think the most important aspect is to demonstrate to the general public, to ourselves, how life on Earth evolved as we see it in the geological record.
Structural geology is obviously important in terms of natural disasters, so large earthquakes, which is what I've been working on most recently. And the processes associated with structural geology, with deformation, are particularly important in that they involve fluids, so water, CO2, magmas, volcanic eruptions, so that the physical aspects of deformation of rocks ties into almost any other discipline.
Well, for research, the area of how glaciers move things and break material up is important, because you can identify then the difference between glacial fracturing and earthquake fracturing, and sometimes that's a question that people want to know. Are these faults made by earthquake and therefore I can't build my nuclear reactor or dam or whatever it is? Is there a danger to the public? Or are these, in fact, natural features that have been caused by glacial activity?
Without understanding how the way the environment reacts to certain inputs, things would go unchecked. Oil companies would just throw waste products out, and the Earth would not be the place that we love today without it. So it's very important to check what other people do. Otherwise, we'd be in trouble.
I think it's important to see the Earth in the context of the solar system. We need to look beyond the Earth and look at other planets. including planetary bodies like the Moon, satellites, and the inner planets, which are very similar in some ways to Earth. And I think with the advent of space exploration and new technologies, we're now able to look beyond Earth and to compare our planet and how it works with the way other planets function. And I think that's where the future lies of Earth sciences, that is looking beyond our planet to the solar system in general. One of the exciting aspects of planetary geology is that there's tremendous potential for economic resources. And this is a very new area of study that we have very limited knowledge right now. But for example, on the Moon, in situ resource utilization is very big, where the aim is to try to extract as many materials as we can from that planetary body rather than transfer them from Earth, such that we use the regolith and we extract the ice from the polar regions and try to live off the land as much as we can. If we go to asteroids in the asteroid belt, many of these are iron-nickel projectiles, which are inherently rich in platinum group elements. There are already companies that are registered with the intent of mining these, and we have to think about how we go about that internationally. Will there be laws? Who owns these assets? What about transporting material from them back to Earth? There's all sorts of exciting technologies to be developed and also exciting planetary geology to be done in order to understand these resources.
I find that space exploration inspires technologies that all of us use every day, things from infrared ear thermometers to memory foam, things like that. So that's something that the everyday person uses in their own life. I also find that exploring another planet actually uncovers information about Earth that we never thought of before. Different processes on Mars, why were they different on Mars? The ones that were the same, why were they the same? Did life ever emerge on Mars? Under what conditions? And what does that say about life on Earth? I think these are all questions that we all ponder when we think about the universe, but also as a geologist, I want to know these things and relate that back to my own planet.
When people are looking at various skill sets amongst people, I came across a very interesting one actually with a banker at a cocktail party. And they were just exchanging what they did, etc. And the banker said, "Oh, we hire a lot of geologists, a fair number of geologists." I said, "Well, why in heaven's name would you hire geologists? Are you using them to examine, stocks in or properties in oil fields or mines?" And he says, no, we turn them into bankers. But the reason we like them is that they're able to come to a decision with very little concrete information. Now, that can't sound like a backhanded compliment, but really what he meant there, or what he recognized there, I think is something that's very important about the breadth of geology and the various ways in which we can use our left-hand side and right-hand side of our brain. And that's that we are never often, or we are rarely faced with the total answer, the total picture. We never have all the information we need. And hence the ability to come to a decision with what we have is what most of the earth science industry is based on.
The earth we inherited locks all her secrets within. Beautiful and bountiful, everything we need for life is here. This is our home and will be for our children and home to their great-grandchildren. Slowly, geologists have bared witness to billions of years of geological change. These people of rock, they have opened our eyes, given us the tools to make sense of our planet, unlocking the past and creating the vision for our future on Earth and beyond.